Through the journey of a digital transformation, containerization offers the promise of agility and flexibility. Kubernetes offers a way to manage that infrastructure at scale. But there's an inherent complexity involved with running containers even with Kubernetes, which brings with it thousands of configuration and deployment options. Finding performance issues can feel like a scavenger hunt, and cloud costs can go through the roof. The companies who will succeed in the digital world will be the ones who are able to launch applications with exceptional customer experience, but which are efficient enough to scale sustainably from the business side. AIOps is designed to find the most optimal solution for your applications running on Kubernetes. This does not mean the program will find just one possible output, however. The Pareto efficient frontier, generated by our machine learning, includes many different optimal outputs. You are in control and get to decide the relationship between variables that will produce the optimal solution for your company.
In this demo, I'll introduce you to the AIOps UI interface, show you a little bit about the experiments. In this case, we've got 4 experiments here on the left-hand side, and I'll show you a simple experiment and how you can interpret the data that's returned. So in this case, we've run the experiment cycle, and the Postgres example will come up and show you a few things about the UI. First, you have the axis for the data. In this case, we're testing duration versus cost. And at the bottom, you'll see the number of trials that we ran, the number of completed trials, and the unstable configurations. So in this case, we had 40 trials, 40 completed, and no unstable, which means from a testing standpoint, we didn't push the edge of what we should have on the parameters. This is an example that we do so that we make sure that people can run a sample application. And here, if you click on one of these dots, each of which represents a trial that was run, you'll find information about what parameters were used during this experiment, and ultimately, which ones are the best ones. You do that by coming up here to the filter and choosing best. This is called the Pareto frontier. This will give you the information about what were the best picked by the machine learning for what you're doing. Normally people pick something that's here on the curve, but depending on what you're trying to do for duration or cost, you would pick at some point along here. When you click on one of these points, it gives you that information. So in this case, let's say we're looking at this. This one and this one are very close in their duration, which means the performance was almost identical. This one was 23, duration of 6. This was a cost of 48, duration of 5. So almost no difference in the duration, but the cost difference was more than twice as much for this example. Here we'll do the Elasticsearch example. Below here you can see that we ran 160 trials, 131 of which completed, which means there was 29 unstable configuration. These unstable configurations may or may not run, but they definitely will not underload, and that's the big takeaway here. Up here you can see that we can still use the best to see the Pareto frontier. But more interestingly, somebody has come in and labeled the active configuration. So this is the configuration that was used before we started optimizing so that we could see the impact. And here you will see the parameters. Now we have more parameters. We have 8 parameters. You can see them here, the various parameters that are in play. Somebody's also come in and looked at the frontier and said, hey, what is the most valuable decrease in cost? And this is the best cost improvement. So for almost the same performance, what is the difference? Well, we'll scroll down, make sure that we see the attributes. This one had a cost of 538 and a duration of 457. If I click on this one, you'll see the changes that happen. I'll do that again so you can see it. Some minor changes in some of the attributes, but the biggest one is that it requires a lot less client CPU and more memory. So this will indicate that this application is more memory hungry and less CPU hungry, or at least in the configuration for the work that we're looking to do here. In this demo, we're going to show you JVM tuning. So for those of you that have Java applications, in this case, we're going to show you bunch of the attributes for a job application. So in this case, we're not tuning so many Kubernetes parameters, In this case, we're actually tuning the actual parameters of the JVM itself. Part of this will be indicated by what's going on for those of you that have done Java tuning. In this case, we ran 120 trials, only of 83 of which completed, 37 were unstable. Those of you that have changed things like concurrent garbage collection threads, heap sizes, things like memory, initiating heap occupancy percentage, those kinds of things that are the things down in the application that really impact your performance and your cost. So in this case, of course, we've got the Pareto front, and then whatever those set of settings are as you move along this curve. In this next demo, we'll show you a voting web app example. This is based on the Docker voting application, which is a sample. They have GitHub that's got this out there. Architecture of multiple pieces, microservices. In this case, it's a voting app front-ended by Python, Redis as an in-memory data store, a .NET worker that processes it, shoves the data into a Postgres database, and then something that will show those results. It's a contrived example, but it's one that's pretty well known in the industry. So in this case, we've done 200 trials and 200 completed with 0 unstable configurations. So in our testing, we didn't push the edges for the parameters that we gave. And because of that, all of these showed to be stable. Just like in other places, we'll show you the best. And if I click on one of these things in the Pareto curve, it'll show you the attributes that we're tuning for here. Things like CPU, memory, replicas of these services. On this one, I'm going to show you another feature of the product, which is a parameter drill down. This is where you get to explore, based on the information that was done during the experiment trials, the information about your actual application and how it's impacted by the various settings. So in this case, we're going to look at throughput, and we're going to select a parameter. These are the parameters that are down below. How does each one of these settings impact the application so that I can learn about my application, because I might make architectural changes based on what I'm learning here. So how does database CPU behave compared to database memory or against the Redis CPU? How do they cluster? Are there any things to gain? In this case, I'm going to show you 2 things that could be very interesting. One of which is the number of replicas for the voting part of the app. In this case, it's pretty linear. We've got 1 replica or 2 replica, and as we go up through in throughput, eventually there's a point where we hit the end, and then the next point that you can get from a performance standpoint actually jumps over to 2 replicas. That's something important to know, that there's this threshold for this amount of throughput. But conversely, you might have something else like the number of worker replicas, where 1 replica isn't necessarily impacted in the same way. In this case, 1 replica can serve to this level of throughput, and then it jumps over, but then it actually jumps back, and this performance is very similar to this performance, which would mean from an architecture standpoint that 1 replica of this service, as opposed to 2, can actually service the need. So depending on what you're looking to do and what your goals are, your application can be better architected based on this kind of information. It gives you visibility into how your application behaves under load that you may not have had previously.